In our last video, we proved these two inclusions, and we proved that the other inclusion was not valid. Now let's see that the finite complement topology is contained in the countable complement topology. Let's see that these two, the complement topology and the standard topology, are not comparable. That is, we will see that this one is not contained and this other one like this either. We will see that the complement topology is not contained in the finite topology, and the same for the rays. The ray topology is not contained in the countable complement topology, and the other inclusion is also not valid. That is a lot of words to say very simple things, so let's actually get to the first proof. That is, the finite complement topology is contained in the countable complement topology. We will again be using that lemma that we saw in the video about bases. So to prove the first inclusion, that is, that the finite complement topology is contained in the countable complement topology, we will just do it with the definition of an inclusion. So we will see that every set in the finite complement topology is also in the countable complement topology. And that is actually very easy, because if we take B, an element in the finite complement topology, then the real numbers minus B, the complement of B, is a finite set of numbers. Let's call them xi from I equals 1 up to some number m. This is finite, but any finite set is also countable. And so this proves that if r minus b is countable, then b is also an element in the countable complement topology. And so we have this inclusion. But now let's prove that this one doesn't happen. So the countable complement topology is not contained in the finite complement topology. What we can do is take some x, for example 0. 0 is obviously a real number, and b a set in the countable complement topology that contains x. For example, we can take b to be the real line, except I can just take any countable set. I can take, for example, the natural numbers greater than 1, and we will use now the counter reciprocal. That is why I'm taking our particular cases. I'm taking a particular x and a particular neighborhood of x, and I will see that there is no element in the finite complement topology that is contained in B and that contains x. This is easy to see, because if, let's call it A, is some set in tau f such that x is in A contained in B, this is what we would require for the lemma to apply and to have the inclusion. Then from this we have that B complement is a subset of A complement. A complement, A is in the finite complement topology, so it is finite. But B complement is the complement of this set. This is just the natural numbers greater than or equal to 1. So this is countable, but it's infinite. And so this would be an absurd, because we have an infinite set contained in a finite set. And so there doesn't exist A in the finite complement topology such that x is an element in A contained in B. So we have that this inclusion cannot happen. That is what we wanted to prove. Now let's talk about the ray topology and the countable complement topology. This one is going to be very simple. Let's see that the ray topology is not a subset of the countable complement topology. Like we did before, just take x to be a number. I'm always taking 0 because it's easy, but you can just take any number you want. And a neighborhood of x in the ray topology could be, for example, minus infinity 1. This is then in tau r, and obviously a neighborhood of 0. But again, if there exists B in the countable complement topology that contains 0, and such that 0 is an element of P subset of minus infinity 1, then, like we said before, we would have minus infinity 1 complement subset of P complement. P complement is countable, and the minus infinity 1 complement is 1 infinity, which is non-countable, that is the absurd. And likewise, the countable complement topology is not contained in the array topology. Very simple, again, we can just take the same set, so x equals 0, and now I have to choose the neighborhood P in the countable complement topology. Now, if I took, for example, the set we took before, B to be the real numbers except the natural numbers greater than 1, then I could have the neighborhood minus infinity 1/2. That would be a subset of P and a neighborhood of 0. So this set doesn't work. I have to be a bit more specific. So the set that I can take is B, the real numbers, except the, for example, 1 over n for L, a natural number. This is a neighborhood of 0 in the countable complement topology. But if there exists A such that minus infinity A is contained in B, then what happens is, well, this one has to contain the 0. So A is greater than 0. But if A is greater than 0, then there exists some natural number n such that 0 is smaller than 1 over n, smaller than A. And so this inclusion cannot happen because 1 over n is an element in minus infinity A, but 1 over n is not in B. So we cannot have this inclusion. So I was able to find for some specific x a specific neighborhood in the countable complement topology for which there is no element in the array topology such that this inclusion is valid. And so we have that this cannot happen. So now that we have finished working with the finite complement topology and the array topology, let's see the countable complement topology with the standard one. So, like before, let's prove that this cannot happen. I'm again going to take x to be 0 and the basis element in the standard topology to be -1, 1. This is an open interval, so it's obviously in the standard topology and it contains the 0. So if there existed P in the countable complement topology that contains 0 and that is a subset of the -1, 1, then the usual argument -1, 1 complement would be a subset of P complement. P complement, because it is in the, here it should be countable complement topology. This is countable, but -1, 1 complement is non-countable. And so this is an absurd, and we have that this inclusion is not valid. Now let's see the other inclusion. The countable complement topology is not a subset of the standard topology. And this will be very similar to what we did with array topology. Again, take 0 and take B, the real numbers, except 1 over n for n, a natural number. Like we said before, if there existed some interval AB in the standard topology, so just a usual open interval such that 0 is contained in AB, subset of B, then we would have that 0 is smaller than B because it's contained in this interval, and so there exists a natural number n such that it's between 0 and B. And so this cannot happen because 1 over n is an element in AB, but 1 over n is not in B. And so we have an absurd, and this inclusion is not valid. So with this, we finish this video, and we will continue with more proofs in the next one.